we've rebooted our system and we've added some storage that we'd like to provision. So this section will focus primarily on provisioning storage on your Linux system. So you have a production system up and running that you need to add storage to from time to time. You may provision that storage after you've physically added it, or perhaps from existing unpartitioned or unprovisioned storage. So let's log in. Here are other users that we've been working with so far. And now we're in. We'll just launch an instance here of gedit. By the way, we can background the process. So if we ampersand it, this will bring up the notes and relieve or release the shell for us to be able to use it. So now this shell, TTY or pseudo terminal number 1, or 0 that is, index at 0 or the first pseudo terminal, is now available for us to use. So with that said, let's cover basic partitioning before we get into more advanced storage management via LVM. So this section surrounds partitions and file systems. And it's important to know how to implement these particular partitions and file systems within Linux systems. So features include ability to provision storage as needed to user space. So what this means is within the Linux file system tree, you can provision additional storage at various mount points. You may also re-provision existing mount points, such as /var, for example, if you've run out of space. So, new storage appears in unified Linux file system. So no need to worry about new drive letters as you do with Windows, for example, such as C, D, E, and so on. You simply provision storage at various mount points. So i.e. attached to mount point. For example, /opt or /var2 or otherwise. So the idea that you can find storage, provision it, make it available, and spread users across it as well as other applications is what makes partitioning and storage management within an Linux-based environment rather flexible. So a number of tasks exist for us. The first is rather simple, and that is to explore the current storage environment. And a number of tools are available to us. One is Df-H with human readable turned on. This enumerates the current storage layout, in particular the user space. So user space storage layout. And by user space we mean storage that's available to users of your system, including root, as opposed to system managed storage such as proc.fs, sysfs, tempfs, or otherwise. So Df-H as a non-privileged user shows us that there's a lone partition that's available to users of our system, root included, and that's the root file system itself, under which all of the mount points are made available, including var, etc, home, user, so on. This particular mount point, root, is mounted at the storage device located in the dev tree SDA1 or SCSI disk 1 or SATA disk 1, and it's approximately 10 gigabytes, of which 6 gigabytes are free. Now supposing we've exhausted or we're nearing the exhaustion of this storage and we need to provision additional storage. How do we go about determining the additional storage? So supposing you've physically added storage to your system. Well, that leads us to a simple command, fdisk. Fdisk with the L option enumerates attached storage. So this will tell us the drives that are attached to our system. Now, if we execute a which fdisk as a non-privileged user, notice it doesn't appear in the path. So the exit status is non-zero. That implies that we should su into the system. So let's su in, or we could have sudoed, and fdisk. Now let's do a which fdisk, and you'll see that it's in sbin, which is a path that's not in the non-privileged user's path by default. So now fdisk L with the list option enumerates the disks that are available. Now, as we look at the disks that are available, we see the default disk, dev SDA. Disks in Linux are indexed normally at S followed by D and a numerical or an alphabetical identifier such as A, and partitions have numerical identifiers, so beginning with 1. So this particular entry is our first disk, dev SDA, and it is tied to the root file system currently. So this enumerates for us, for example, the following. This is the first SCSI / SATA hard drive, dev.sda. Now dev.sda may be partitioned in a number of ways. So if we further read below, beyond the geometrical layout of the disk, we see exactly how the disk is segmented or partitioned. So here we see dev.sda is broken up into 3 partitions, SDAs 1 through 5, skipping of course 3 and 4. SDA 1 is where the root file system is tied. It is also flagged as the boot partition. So this is where the Linux kernel expects to find, for this system at least, the root file system. It boots from here. So when we enumerate the contents of /boot, we're really referencing dev.sda1 on this system. For many other systems, boot is a separate partition altogether, such as dev.sda1 from root, which may be dev.sda2. On this system, since the storage we provisioned originally or initially was so meager, everything was lumped into one partition. So that's dev.sda1, and it is of type 83, which is a Linux file system. So let's just take this particular content and dump it into our notes just as a quick discussion point. So dev.sda1 is flagged bootable. It starts at the first block and it runs through the 1246 block, and the geometrical layout per hard drive is of course dependent upon the hard drive, but it's spelled out in the fdisk dump. The heads, sectors or tracks, and cylinders are spelled out, and the number of, or the size associated with each block times the number of cylinders will get you, times the number of heads will get you the storage that's available for this particular system. This system is using 512-byte sectors. So for example, when we looked at a directory earlier and we saw 4096 and the fact that it's occupying 8 blocks, let's just segue for a second, but let's take a look at some entries in this particular directory. So let's stat the temp directory because it's a directory that is readily available. So we see that, for example, the temp directory occupies 4096 blocks, or 4K bytes, that is. And so not 4096 blocks, but 4096 bytes, or 4K bytes, which spans 8 blocks. Now, each of the blocks, according to the fdisk dump, occupies 512 bytes, which makes sense. 8 times 512 bytes gets you 4096 bytes. So our directory entry occupies 8 of the blocks provided by this particular file system. So fdisk L again, 512 bytes, smallest size, and the directory entry uses 8 of them. And for that matter, let's take a look at the various files in this directory. Stat, let's say for example, temp.gz. So temp.gz uses an IO block of 4096 4K blocks, and it's using 12,192 blocks. So you multiply these out and you get the full size of this particular storage, which is represented here in its absolute byte size. So fdisk L again enumerates the storage that's available. And as we can see, for the first disk, as we scroll up, SDA1 is the bootable disk. SDA2 is an extended partition. It's simply a placeholder which references the remainder of the disk. With traditional PCs, we're limited to the number of primary partitions that we may define, as well as extended partitions, but we're allowed to define more extended partitions than primaries. With respect to primary partitions, we're limited to 4. So the installation process configured one primary partition, which is bootable, which is an absolute must on x86 systems. You must specify at least one primary partition that's bootable in order for the system to boot, followed by an extended placeholder. If you look at the block range, it picks up where the first partition SDA1 leaves off at block 1246, and it ends at the end of the disk 1306, which is the remaining space, which tells us that the bulk of the disk is really associated with dev.sda1. Now within the extended partition dev.sda2, which is labeled as extended, which is type 5, we see that there is a lone partition labeled dev.sda5, and it runs the range from where the first partition ends, 1246, to the end of the disk, and it's a swap partition. So this is our swap partition that was configured during installation. Swap partitions in Linux are of type 82. Now you may be wondering, why is it that the swap partition is flagged or indexed at 5 as opposed to 3? And that is because traditionally with PCs, x86-based systems, 4 primary partitions are allowed. So it's a reservation and an acknowledgement of the fact that there are 4 primary possible partitions. So extended partitions tend to be indexed at partition number 5 for traditional historical reasons. So with that said, this is the first disk's layout. Now let's move on. Here are 2 other disks, Dev6x and Dev6x. They're of course presented out of order, but we can copy and paste. In fact, Dev6x, we actually provisioned 3 of them, so there are 3 additional partitions available. Let's go ahead and include this in our dump, Dev6x, and they're of equal size purposely. We provisioned 3 extra 10 gigabyte segments for our usage. And notice it reads that it doesn't contain a valid partition table. It's yet to be partitioned, which of course is the case because we just provisioned the storage. So when you add storage physically to the system that does not contain previously defined partitions, fdisk registers that visually that it isn't partitioned, and as a result needs to be partitioned in order to make it usable by the operating system and by users of the operating system. So here are the additional disks, which are 10.7 gigabytes roughly each. They don't contain partition tables. Now there are 2 tools that we can use from the shell to create these partition tables. We can use fdisk itself or parted. So either tool would be the tool to go with to create an extra partition. Now before you create partitions, you need to know what you're creating the partition for, what type of data you intend to store within the partition. So you take a look at your storage configuration, you look at your root file system, for example, you look at these top level directories, bin, boot, dev, so on and so forth. You typically don't move the items such as dev and etc from out of the root file system. These are considered essential. There are a number of directories that are considered essential that should be a part of the root file system, including bin, dev, etc. Others that you can move include home, for example, user, var, opt, which is this particular item. But the others like mount and so on, we normally leave within the root file system. Serve can also be moved. In other words, user space mount points can be moved, meaning data that can be stored anywhere on your disk or across your disks without regard for the kernel at boot time can be moved anywhere. So long as the kernel needs to reference that data, such as is the case with key utilities from bin, configuration files from etc, devices that are auto-populated by udev when the system comes up, the boot partition of course, then that's something you don't want to move out. You can move the boot partition, but you have to make sure that when it's time to boot the system that boot partition is made available. Otherwise the kernel in the initial RAM disk will be unfound. So it becomes a question of what else makes sense to move out of the root file system to save space. Now there's a utility that can quickly tell us which of these directories perhaps may be a good candidate to move outside of the root file system, and that's du. So for example, as a second task, we could list find a suitable mount point to move from the root file system. Using du with, let's say, the CHS option, this will return in human readable format a summary of the storage occupied by a given directory. So we'll just indicate directory. Will tell us the storage occupied by that directory. Now var is normally a good candidate because of the variable log data that it holds, but of course it's largely only large when the system's busy. So let's du chs var, and that's going to be off of the root of the file system. So it's 257 megs. Of 10 gigs, that's large. And let's take a look at user, which contains applications. This is going to be bigger than var. It's 2.6 gigs. So user could be a candidate, but we'd have to move this carefully. Perhaps an easier move at this particular point without too much hassle would be var. So we could create, let's say, var2 as a mount point, create a partition and file system, and mount var2 on it, and then copy the contents of var over to var2, and then relabel it accordingly, thus moving var to a separate hard drive altogether. So we could make that our task. So let's go ahead and note we've identified, and we'll just indicate that we've specified /var. And now our next step is to begin the process of moving the contents of /var to a new hard drive. So a number of steps are involved. We need to create a partition. So first step is to use a tool like parted, indicating the disk that you'd like to partition. This will be Deb6x, for example, since it's the next available disk. We could optionally use fdisk or the graphical equivalent. So let's go ahead, copy this, paste it to the shell. You need to execute parted as, of course, root in order to influence changes. Now notice parted is not available. So let's go ahead and run fdisk. We'll install parted momentarily and use it to create a different partition. So we'll fdisk instead, Deb6x. So let's change out parted, fdisk, Deb6x. Now this provides us or places us within the context of this particular drive, Deb6x. Once within the context of a hard drive, M gives you help, and you'll see there are a number of options, including P to print the partition table, and currently the partition table is empty, so we'd have to use N to create a new partition. Here we see the geometry of the disk, which tells us the size, which gives us a clue as to the sizes of the partitions that we can create. And there are other options, of course, such as the ability to delete and assign various types and so on to the partitions created. Now, when creating a partition, whether using parted, a GUI tool, or fdisk, we need to determine whether or not it's going to be primary extended. Since there are no partitions on this drive, Deb6x, the first should be primary. So let's create a primary partition indexed at number 1. As we approach the limit of 4, the hard limit of 4 for primary partitions on the disk, we can then decide to create extended partitions. So the first cylinder, you can create a partition anywhere on the disk, akin to having a song anywhere on a record, or anywhere on a CD if you'd like, or anywhere on your portable player that's solid state based, meaning you don't have to start at the first sector or the first cylinder of the disk. You can start in the middle or towards the end if you'd like. Normally speaking, under common circumstances, it makes sense to index your storage at the beginning of the disk. So we'll start with cylinder 1. Now, a number of ways exist to specify the number of cylinders that should be occupied. You can use up all of the cylinders of the disk, of which there are 1305. Or you can specify a storage using, for example, size, a familiar size, measured in kilobytes, megabytes, gigabytes, for example. So supposing we wanted, of the 10.7 gigs, 5 gigs. We could indicate 5GB, for example, or 5G, and this will create a 5 gigabyte partition by measuring out the requisite number of cylinders. Notice by default it's flagged as type 83 Linux. So this is the right partition. And also notice that it's been indexed as partition number 1, because when we indicated that it's the first partition, that number was married to SDB. So now SDB1 is the first partition, which happens to be primary, and it need not be bootable because we have a hard drive with a partition on the system that's bootable. So it starts cylinder 1, ends at 654, leaving roughly half of the cylinders free for subsequent partitions. So it's of type 83. So now the partition is flagged in the partition table, and when we save the changes, P to print and M to help and W to save the changes, this will write the changes to the hard disk. Now we always caveat or warn that when using tools like fdisk, sometimes the kernel will be unable to write the changes immediately to the disk or have it available to the user tools such as make2fs to create a file system, thus warranting or justifying a reboot or requiring a reboot for that matter. So let's go ahead and write the changes, and so far so good. It didn't complain. Sometimes, however, Linux will complain, requiring that you reboot the system. This is why the suggestion is that if you provision new storage, you do it in single user mode, with very few processes connected and running, and no users connected and running. But so far this looks like it's run successfully. So to provision a partition, we've executed fdisk, and then we executed the following options: P to print, N for new, P for primary, 1 for the number, and we started at the first cylinder, and then we included plus 5G to indicate 5 gigabytes, 5 GB creation. And then, let's not forget, we also wrote the changes to the hard drive, and the kernel was updated as a result. So now that the partition exists, if we rerun fdisk with the list option, you will see for dev.sdb there exists one partition. You can zero in on a particular disk by just indicating the name of the disk in the dev tree, dev.sdb. This enumerates partitions that pertain exclusively to dev.sdb. So again, there is the lone partition. Now the next step in the process is to overlay the partition with a file system. File systems make it possible to keep track of all of the metadata associated with the files that we've grown accustomed to with operating systems. Windows, Linux, Solaris, Mac OS X, so on and so forth. So here's a bunch of stuff in this directory. What is all of this information? Permissions, user and group ownership, timestamps, as well as inodes. If we stat, for example, 1-2.text, we see all sorts of useful metadata. These metadata are brought to you by the file system. So without a file system, you'd need some other means of maintaining metadata. Some applications, like Oracle DB, for example, can take advantage of storage sans a file system because the application maintains the requisite metadata directly with the disk. Those particular applications are known to access raw storage because it isn't overlaid with a file system which keeps track of metadata. In addition to this metadata, additional metadata such as quota information is kept track of. So a number of services are provided by file systems. Quotas, access and modify and change time with various precision lengths depending on the file system type, the access permissions, the number of links, the blocks. All of that is provided by the file system. So the next step for us is to create a file system on dev.sdb1. And let's just note, file systems such as ext3, ext4, and for that matter even NTFS from Windows, UFS from Unix, etc., provide key metadata services, including, but not limited to, access, change, modification times, permissions, and let's just take a look at our stat, UID, GID, for example. So UID, GID, inode information, and let's see, quota information, etc. So anything that is associated with a file object, whether it be a directory file, character device, block device, the file system keeps track of for us. And this is why it is important that we overlay partitions with file systems. A partition is simply a mechanism, just like in the physical world, of segmenting off an area of something. So the hard drive has a surface area. A partition says, give me this fraction of the disk. And then a file system says, I'll keep track of, via metadata, the information on that particular segment. So with that said, how do we make file systems? Well, a number of tools exist and a number of formats exist. By default, Make2FS is the tool that exists which allows us to create file systems or to overlay file systems. Make2FS supports a number of options. You can come up with a useful set of options by manning or executing man Make2FS to create your overlay. Now, Make2FS is capable of creating ext2 as well as 3 and 4 file systems as indicated. But there is another way, an alternate way of calling make2fs, which automatically creates the desired file system type, and that's using makefs dot the extension that's of interest. So if we tab out makefs, you'll see the various file systems that we may reference. So, for example, makefs ext4 followed by the partition location will create an ext4 file system for us. So this is one way to reference the file system that's of interest to us, and that's to create it using makefs.ext4. So that's what's of interest to us. Let's go ahead and do that. Otherwise, if you simply use make2fs, then you'll need to enable the options that are called by the shortcuts, such as J for journaling, for example. So the next step, or as part of C, so let's call this C1, is makefs.ext4 dev sdb1. And this generates an ext4fs on partition dev sdb1. Once the file system has been generated, we may then mount it and use it, meaning begin the process of read and write on the particular file system. So let's go ahead and make fs, and the various inodes are generated. So when you run makefs, it has a default block size that it uses, 4K block sizes, which can be altered, by the way. So if you have high performance storage, for example, like RAID, perhaps you want to use 8K block sizes, which will provide faster access to the content, sacrificing storage, of course, but nonetheless being much faster, as the operating system can process larger chunks. But this uses 4K size blocks by default, and we see the number of inodes that are generated, in this case 8016. If you recalled, we mentioned that inodes restrict, or in this case actually more, those are the inodes per group, but there are a number of groups that are 328,000, that sounds more like it, 656 inodes. We mentioned that inode numbers are repeated, and that's because they represent a particular file system, and they limit your ability to create hard links across file systems as a result, because the numbers are repeated or are not unique. So each file system uses similar inode numbers, 1 through n, for example. So now this journaled file system has been created. Journaled file systems are fault tolerant, so in the event of an abrupt failure or loss of power or otherwise to your system, then it is transaction oriented. It will be able to replay your changes or to not commit corrupted data to disks, so the chance of corruption is small to nil. So with that said, we now have an ext4 file system on dev sdb1. So our next task is to create a mount point and then mount the file system and then update our system table. So D will be to create mount point and mount the device. To do that, we'll make directory var, let's call this var2 since we're going to be offloading var, and let's mount dev sdb1 to var2. And then we'll do a df-h to see what the kernel sees in terms of file systems that are available. So there's dev sdb1. So it's now available at var2. Now how do we learn more about this particular mount point? Well, we could use mount, for example. Mount shows that dev sdb1 is of type ext4 and it's mounted read-writable. Mount can also be used to remount the device, for example, as read only in the event that you are experiencing problems. And you can also attempt to remount on the fly, but if it's mounted, it throws an error. But now var2 is available. We can start to populate it with data. Now the system's running, so if we copy content now, it will not be as useful to us. There is a process, rsync, which can track the changes for us. So we can start in a multi-user run level, such as run level number 2, and then finish in run level number 1 using rsync, for example. Or we can simply move to run level number 1 and do a wholesale copy of var to var2, and then we'll have this available. Now, rather than go through the whole boring process of copying at this particular point, let's ensure that var2 will be persistently available across system reboots. So the last step in file system provisioning is quite simply to update etc/fs tab. This is the file system table. So file system table. And this ensures that fs is persistent. Regardless of the fs, it could be Samba and fs across the wire using any protocol supported by the Linux kernel. This is the file that you need to update. So let's nano etc/fs tab, and we'll copy an entry, and we'll ensure that it's mounted post root, for example, in this particular location. We could even do it after swap, but if we want to keep it within the user space area, this would be an ideal place to do it. Here are the fields that are of interest. The file system. So in this case, we know that the file system is Deb6x. Now we know this is subject to change. This is why the UUID is one sure way of ensuring that regardless of what the kernel calls the file system, that it is found uniquely. And of course block ID would help us there, but simplistically speaking, this is the way you'd reference the mount. So Deb6x should be mounted to var2, and it is of type ext4 or default. You could just simply say defaults, and that will leave it up to the kernel to figure out what it is. Or if you know it's ext4, certainly label it ext4, either or. And what should happen in the event of any errors or any problems, or just go with the defaults, and whether or not it should be dumped or checked upon booting, and we'll tell it to check it. Let's check it as number 2 after the root file system. So let's just include an entry here, Linux CBT classroom mount for var2. This is temporarily var2. Once we've moved the content, then we'll relabel this as var, and then when the system comes up, var will no longer exist off of the root file system, and then we can remove it altogether, saving that space while it's still labeled var, of course. So this is our mount point. Now before you reboot your system, the thing to do is to test that this will mount. So let's save the changes and unmount and remount. So the next step in the process, test auto mounting by unmounting and remounting via etc/fs tab, because again the idea is to pretend as if you're working remotely with the system and you don't have physical access, lights out configuration if you will, and any little mistake you make is likely to cause the system to have trouble or experience trouble booting. So to unmount an item, currently if we mount, we see that it's mounted. We simply unmount, either specifying the dev tree location or the mount location in user space. So let's umount var2 since it's fewer characters. We'll echo the exit status and then rerun mount, and you'll see that var2 is no longer available. df-h confirms that, and an lsl var2, well, doesn't exist. So, or no information's there. So it's been unmounted. Now to remount, we simply mount A. This reads the contents of etc/fs tab, and barring no errors, will remount the item for us as it has. So mount will also confirm that it's available. So the next step here is a combination of umount var2, mount all, and let's just note, causes mount to read the contents of etc/fs tab. So that works. Now that raises the question, what about the block ID notion? We know that there's a unique ID or UUID, a globally unique ID associated with devices in Linux. So there's a command, block ID, and if we execute this against Deb6x, a unique ID is returned. There's a UUID. So if we reference this UUID, it'll remain true, and if we reference it in fs tab, it'll mount that way. So let's go ahead, nano exclamation nan, and rather than clobbering this entry, let's Control-K, Control-U twice, comment one of them, changing this item. Notice it isn't protected with quotes, so we'll ensure not to protect it with quotes. Now we have mimicked the UUID reference. Notice it also applies to the swap entry. This UUID way of mounting devices is superior because, again, if the kernel or an administrator inadvertently reconfigures the dev tree locations, then the UUID will clear matters up and ensure that the appropriate storage is mounted at the appropriate mount point. So And there are all sorts of security issues surrounding this to ensure that you mount the right partitions at the right mount points so that the right people are, or the authorized people are able to access their data. So let's save the changes. And again, we'll need to go through the process of umount mount. So let's umount var2 followed by a mount all, and then an echo of the exit status. Now let's mount, and indeed, there's dev_sdb1 again on var2. So again, it's up, it's working, this is looking good. Now, one other thing we should mention. We provisioned 3 extra disks. As you can tell, fdisk-l shows that we have, in addition to dev_sda, dev_sdb, which we've just configured, and devs_sdc through d. How do we know that these disks are available when a system has come up? Rather than, or let's say we didn't execute fdisk-l, is there some other indicator, some other means of knowing what the kernel saw when it booted the operating system? If you execute yet another command that we haven't looked at, dmessage. Dmessage dumps, to stand it out, what the kernel saw, how it initialized the system. So as you scroll through the dmessage dump, you will see the storage, the hard drives that were detected, and their characteristics as the system came up. So for example, here's dev_sda. It found SDA and its attributes, and it saw it as parallel ATA, and so on and so forth. And then, as in fact, this might be a different device. It saw it as SCSI, fast wide SCSI, 80 megabytes. So, and as we keep going through the list, we see that it also found dev_sdb and characteristics of dev_sdb, and then dev_sdc. So the dmessage dump, and you can dump dmessage to less to see it one page full. It always reflects the most recent invocation of the kernel, showing you what the kernel saw when the machine was initiated. The version of the kernel, so on and so forth, processor information, the BIOS, Phoenix BIOS. But as you get past that boring stuff, which normally works, how much memory is available on the system, you then get into the juicier information, which includes the storage that was found on the system when it was brought up. So you scroll through this, get through the PCI bus, the different devices that are connected, and you'll eventually hit the storage. And that's the important information. So what this tells you is that from time to time, here's the network driver information, PCNet32. From time to time, you should run dmessage on your system and evaluate. ETH0 is associated with this PCNet, by the way. So this is the driver, the card that's registered for ETH0 for this particular instance of Debian Linux. So from time to time, peruse the output of dmessage, because it'll reveal to you what was found on the system at the most recent invocation, or during the most recent invocation. And in this case, since we know that storage has been added, SDs C, B, and D. And notice the order in which they were detected. C, then, as we can see, B, then D. So that's the order in which it was detected. So that's how you determine what the kernel saw when the machine was brought up. So let's just note, use dmessage to peruse the view of the hardware from the perspective of the kernel at last boot. That's the output that's provided to you. So that is the process of provisioning storage. You repeat this process for your other partitions. And that's a simple way of provisioning ext4 storage. Now, one quick note before we leave this section and move on to more storage-related issues. So now we have this item mounted, var2, and it's of type ext4, indicated by the dump from mount. We mentioned that ext4 confers additional features and advances such as nanosecond precision and timing of objects created files. So let's see what that means. That's just one simple feature that comes to mind. So let's touch a file, test.txt. Now let's stat it. And notice the nanosecond precision. Nanosecond precision simply means 10 to the negative 9th, so you should see 9 digits to the right of the decimal point. This information is not present within ext3. So for example, let's stat initrd.image. Notice that to the right of a decimal point, it's all zeroed out. So not even microsecond or millisecond precision is preserved with ext3. ext3 and ext2 preserve precision to the second. ext4 preserves it to the nanosecond. Big difference, especially in today's heavily web-connected environment where numerous hits, thousands of hits, maybe even more to a web server per second can distinguish reads and writes. Then we need a more accurate means of measuring the contact with the data points, and nanosecond precision provides that for us. So ext4 provides us. Let's just note that ext4 provides, among other features, many other features, including directory depths, number of files, so on and so forth, nanosecond time precision, whereas up to ext3 was second precision. So that's one key difference between the types. So enough time on creating simple partitions. Let's move on.